Okay, so let's do some examples in this video of how we would create a model, an exponential model, given some information. So let me read this to you. It says, in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an algebraic function, capital N of t, representing the population of deer over time t. Okay, so now, obviously our independent variable is going to be t, right? Time. And so let's say we have n. N equals the population of deer. T is number of years. That's going to be our independent variable. And so we know it's growing exponentially, so we know that our model is going to have this form. Okay, it's going to have an initial population size, so it's going to have A, right? Now, A and then B to the T, right? We want to use T. Okay, now, what do they give us? Well, they introduced 80 deer in 2006. So there's one data point. And then by 2012, it had grown to 180. Okay. Now, it says, let's see here. Okay, so now, since this is when the deer was introduced, right? The deer was introduced to this refuge. So that means this is going to be times 0, right? So let's t equal the number of years from 2006, because that's when it was introduced, right? Before that, we're assuming there were no deer. Okay, so the initial population of deer was 80. And that was in 2006. So let's set up our t value instead of 2006 to 2012, then this is going to be 0. And then how many years after 2006 is 2012? That's going to be 6. So that's what we're going to use for our data points. Now notice that we have a 0, comma number here. So this is our y-intercept. That means 80 is our A, right? So we already know A equals 80. So guess what? All we have to do is take this point, plug it into this equation with A equal to 80, and solve for B. So let's do that. So we get f of t equals 80. Oh, by the way, they want n equal to number of deer. So in this case here, instead of f, the number of deer is a function of time. So instead of f, which is what we use generically, we're going to use n, capital N. Okay, so that our model so far is going to be n of t equals 80 b to the power of t. And so now what we're going to do is we're going to use this point in here. And so that means we have 180 equals 80 times b, raised to the power of 6. Okay, now, so now how do we solve this? Well, let's do some algebra. So this is, we're going to divide both sides by 80. So this is going to be 180 over, well, let's write this the other way. Let's switch this around. So we're going to get b to the 6th power equals 180 over 80, right? Which is going to equal, let's see here. Both of these are divisible by 20, right? So if we divide both these 20, we get 9/4. And so now if I take each one and raise it to a 1/6 power, right? So now if I raise this to 1/6 power, so this is going to be b to the 6. I'm going to raise this side to the 1/6 power, and then I'm going to raise this side to the power of 1/6. Well, using the power rule, we get 6 times 1/6, which just gives us b. And so we get b equals what? 9/4 to the 1/6 power. And so now that's something we can plug into our calculator. And so b is approximately, out to 4 decimal places, 1.1447. So this is going to be approximately 1.1447. So that is b. So that means that our model is going to be n of t, oops, n of t is equal to, well, 80 times 1.1447 raised to the power of t, and this becomes our exponential model that models the growth of deer in this wildlife refuge. Okay, now, we can graph our model to observe the population growth of deer in the refuge over time, and we can notice that in the graph, of course, we can see that even based on the model, that this is going to have what? It's going to grow to infinity, right? Obviously, theoretically, but not practically, right? Based on resources, food, water, habitat, and things like that. But just from a pure mathematical standpoint, this is going to grow to infinity. So this is going to have a domain, right? The domain is going to be all real numbers. And the range, now here's the thing, the range, when obviously time can't be negative, so when time is 0, we get 80. So this is going to have a range of 80 or higher, right? So that's going to be the range. So it's going to go from 80 to infinity. Okay? And the domain is 0 to infinity, right? Because you can't have negative time. Okay, so let's do another one. We have a wolf population. Or you know what? We'll save that for another video. See you next time.